Hello everyone, this is Dr. N.G. Praveena working as Associate Professor in the Department of ECE at R.M.K. College of Engineering and Technology. In this video lecture, I am going to discuss about the current shunt feedback, which is otherwise known as shunt series feedback. The highlights of this video lecture are the block diagram of the shunt series feedback amplifier will be discussed, and the analysis of the input resistance followed by its output resistance will be discussed. In this slide, we are going to discuss about the block diagram of a shunt series feedback amplifier, why it is named as shunt series feedback amplifier, what is the nature of the sampling signal and what is the nature of the mixing signal, and the gain with feedback, gain without feedback, feedback factor, all those things we are going to discuss in this slide. Now, when you look at this block diagram, we have two blocks here. The one is your amplifier block, the other one is your feedback block. The amplifier block will vary, depends upon the type of the feedback we use. Since we use a current shunt feedback, the amplifier what we use is your current amplifier. And you have your feedback network. The feedback network is constructed using passive elements, which is nothing but RLC. Right? And the next thing is, we say this type of feedback follows current mixing and current sampling topology. Why it is said to be a current mixing and current sampling topology? Here the current is taken as a sample. Here we take a portion of the output signal. Here the portion of the output signal is nothing but your current signal. That is why we name it as a current sampling topology. And the feedback signal is IF. IF is equal to beta I naught. We take a portion of the output signal, so IF is equal to beta I naught. Now, what type of mixing we do here? We do a current mixing because we mix always the known signals, always a common signals. You cannot mix a voltage signal with a current signal. You always mix a common signal. So here the signal is nothing but my current signal. Source signal is your current and your feedback signal also current. So it is named as current mixing, current sampling topology. The next comes what type of connection we implement in this block diagram. From the block diagram, it is so clear that we use shunt connection at the input. It is a shunt connection at the input and series connection at the output. Hence it is named as shunt series feedback. And the next thing is, we should know the basic parameters that is required for this feedback amplifier. Since it's a current amplifier, the first thing is we should know what is AI. Current gain without feedback. AI is nothing but the gain of the current amplifier for without feedback. So gain is normally named as output by input. So output current by input current. So AI is equal to I naught by II. The next one is beta. Beta is nothing but the feedback factor. So it is nothing but IF by I naught. So beta equal to IF by I naught. The next parameter is nothing but the gain with feedback. So how you write gain with feedback? It is nothing but AIF. So AIF is equal to I naught by IS. Now when you compare your AI and AIF, two things you should understand. What is AI? It is a gain without feedback. What is AIF? It is with the feedback. And the next thing is, the denominator of this expression is nothing but here II, here you get what? IS. Okay. The next thing is, we are going to discuss how to derive the input resistance for with feedback. We have taken the same block diagram. Okay. We have converted the block diagram into an equivalent circuit diagram. I have replaced the current amplifier, okay, by its equivalent circuit, which has been shown in the box, dotted lines. Right? So here the input signal is your IS and the feedback signal is IF equal to beta I naught, and the circuit which has been shown, okay, in the dotted line is nothing but your equivalent circuit of your current amplifier. Now we derive the expression for RIF. So how we derive resistance? Normally voltage by current. So input resistance RI, voltage, input resistance voltage by input current. Since it is RIF, we write that as VI by IS. So input voltage divided by the current, which we consider for the feedback. So VI by IS. Now focus only on the input circuit. Look at the input circuit. So simple. If it is a Thevenin, you apply KVL. If it is a Norton, you apply KCL. When you look at the input circuit, it is nothing but a Norton circuit. So apply KCL at the input circuit. So what is the entering current and what are the leaving current? Look at the circuit carefully. The entering current is IS, whereas the other two currents are leaving current. So I can write the expression such as IS is equal to II plus IF. Now replace your IF, your feedback signal, alright, feedback signal with your feedback factor value beta. So I can rewrite this as IS is equal to II plus beta I naught. Now focus on your output circuit. How to write I naught in terms of the current gain without feedback. So I naught can be written as AIII. So I have written AIII. Now look at this expression. II is common. You take II common outside, right? So from this one, what is the thing that's required is you need VI by IS. So you have IS, but you don't have VI. Instead of that, you have II. So replace II in terms of VI. How to replace II in terms of VI? Current can be written as voltage by resistance. Since it is II, what is the input voltage? I have VI. What is the input resistance? I have Ri. So how I am writing this here? IS is equal to VI by Ri into 1 plus beta AI. Now rearrange the terms. Write in order in such a way that to get the expression for RIF. So RIF is equal to VI by IS is equal to RA divided by 1 plus beta AI. Now you must compare the expression, okay, with respect to two parameters. One is RIF, the other one is RI. What is RIF? It is the input resistance with feedback. What is RI? It is the input resistance without feedback. When you compare this expression, it is so clear that RIF is very lesser when compared to RI by how much times? It is 1 plus beta AI times. Okay, right? So what type of feedback we are discussing right now? Current shunt feedback. What type of mixing we do here? Shunt mixing. So if you do shunt mixing, the input resistance will be reduced. So RIF will be lesser when compared to RI. The next thing is we are going to discuss how to find out the output resistance with feedback. For finding the output resistance with feedback, we apply 3 steps. The first step is we remove the load resistance RL. So I have removed the load resistance RL. The second thing is we have to remove the source. If it is a voltage source, short circuited. If it is a current source, open circuited. Since I have a current source for this, I have made it as an open circuit. The third one is you connect a voltage source at the output. Here we have connected V, okay, at the output. Now look at the circuit. Once again, a simple concept you should have a clear understanding. If it is a Thevenin circuit, you apply KVL. If it is a Norton, you apply KCL. Focus at the output circuit. Look at this. It's a Norton or Thevenin. So simple. It is a Norton circuit. So you apply KCL at the output circuit. Now when you apply KCL at the output circuit, what is the entering current? What is the current that is generated from voltage source? It is I. I equal to, one is the current flowing through R0, the other one is the current source AIII. So I am writing this as I equal to V by R0 minus AIII. So take this as your basic equation for determining the output resistance. Then from the fact we know that we have made the current IS as 0. So we know that IS is equal to II plus IF. Since IS is made 0, I can write IS is equal to minus IF. So replace IF with respect to beta. So I can write down minus beta I naught, or otherwise I can write beta I. Now substitute your second expression in your first expression. So you get I equal to V by R naught minus beta I AI. Now group I on one side. So I'll get this expression. From this I'll take I common. So I'll get V by R naught is equal to I into 1 plus beta AI. So from this you write down what is V by I. So R naught F is equal to V by I equal to R naught into 1 plus beta AI. Now look at this expression. Once again you focus on two terms. One is R naught F, the other one is R naught. What is R naught F? It is the output resistance with feedback. What is R naught? It is the output resistance without feedback. When you compare this expression, it is so clear that R naught F is very much greater than R naught. What type of sampling we do here? Current sampling. So if we do current sampling, obviously the output resistance will be higher, okay, for the feedback when compared to without feedback. followed by the applications of the feedback amplifier. We apply the feedback concepts, okay, in so many applications. The first application we use is in RPS, in regulated power supplies, okay, we use the feedback concepts. And the second one is we apply these concepts in amplifiers where large bandwidth is required. For communication purposes, okay, we use this type of feedback concepts. And last one is we use in electronic amplifiers. Hope you understood the basic block diagram of a current shunt feedback amplifier, followed by the input resistance analysis and followed by the output resistance analysis. Thank you all.